Okay, so we are now going to start our first set of exercises in calculus. So the first one is quite easy. We have been asked to express 1 divided by 9 as a repeating decimal using a bar to indicate the repeating digits, and also we have to find the decimal representations of these numbers. So we can just simply write without writing anything much. This is actually the decimal expansion of 1 divided by 9, and so it can be written like this. The bar indicates that 1 is the digit that gets repeated, like that. The repeating digit in these cases turns out, in each one of them, turns out to be the numerator itself. And is this. Like that, there is another one which is similar. Express one divided by 11 as a repeating decimal using a bar to indicate the repeating digits. And also, along with this, we have to find the decimal expansions of what are the decimal representations of 2 divided by 11, 3 divided by 11, and 9 divided by 11. So in this case, the expansions look like this. One upon 11 is this 0.09 bar. So 09 is the block of digits that gets repeated. That means this is 0.090909 and so on. Two divided by 11 turns out to be 0.18 bar. 3 divided by 11 equals 0.27 bar, and 9 divided by 11 equals 0.81 bar. Okay, so these are the decimal expansions. Next, we have some problems involving inequalities. 3. Exercise 3. If 2 is less than x and x is less than 6, that means x is some real number lying between 2 and 6 in this sense. Then which of the following statements about x are necessarily true and which are not necessarily true? So these are the statements. A, 0 is less than x, x is less than 4. B, 0 is less than x minus 2, which is less than 4. C, 1 is less than x divided by 2, which is less than 3. Then D, 1 upon 6 is less than 1 upon x, which is less than 1 upon 2. E, 1 is less than 6 by x, and that is less than 3. F, the absolute value of x minus 4 is less than 2. There are even more. G, minus 6 is less than minus x, and that is less than 2. H, minus 6 is less than minus x, and that is less than minus 2. Okay. Which of these statements are necessarily true means which of them are consequences of these inequalities. That is, which of them are following from these inequalities. So, for example, if we consider the first one, if you start from these inequalities, you can see that it's not necessary that we must have these inequalities. For example, you can take x equal to 5. This value satisfies these inequalities. However, this value clearly does not satisfy these inequalities. Although 5 is greater than 0, but 5 is not less than 4. So, this is not necessarily true. It's not a consequence of those inequalities, the given ones. The statement in A is not necessarily true because 2 is less than 5 and 5 is less than 6, but we can write like this: 5 is not less than 4. You can verify. We are now going to see, although we won't write it elaborately, all the statements, how they are following. All the remaining statements follow from this initial one. We will just quickly see why that is true. To derive this one, what you do, you subtract 2 throughout, which we can do. The rules for inequality, manipulating inequality, allow us to do so. Doing that gives us, on this side we will have 0, here we will have x minus 2, and 6 minus 2 is 4. So that gives us b. So b is a consequence of the given inequalities. What about c? You divide throughout by 2. That also we can do, because 2 is a positive real number. Doing that gives us this. So this is also a consequence of the given inequalities. Then d, you take the reciprocals of all the terms, that will reverse all the inequalities. And note that we are able to say so because x2 is positive, and since x is greater than 2, x is also positive. So because both 2 and x are positive, that is, they have the same sign, so we can take their reciprocals and they will satisfy the reverse inequality. A similar argument applies to the second one. So that gives us this. Which is the same as this one, just written in another manner. So this is also a consequence. E. For E, what we do, we can start with these inequalities, because these imply these, and they will now imply this one. How? You multiply throughout by 6. That will give us this, which are nothing but these inequalities. So that is also, after all, a consequence of the initial inequalities. Then f. What about f? Subtract 4 from all the terms. Doing that gives us minus 2 less than x minus 4, that is less than 2. 6 minus 4 is 2. And this is in fact equivalent to this. So that's how we are getting this as a consequence of these inequalities. Then multiply throughout by minus 1. So this is f. Multiply throughout by minus 1. That gives us what? Minus 6 is less than minus x, that is less than minus 2. And this implies minus 6 less than minus x less than 2. That is because if minus x is less than minus 2, then minus x is automatically less than 2, because minus 2 is less than 2. Note, however, that you cannot go in the other direction. If this is given, then we cannot have this one. For example, you can substitute 0 for x. Then these inequalities are true. Minus 6 is less than 0, that is less than 2. However, here you cannot take 0, because this second inequality will be false. But that's not what we want. We want this one, and this is a consequence of these inequalities ultimately, and that's why we are getting this. And even before getting this, we have actually got the h part. So h part is here itself. So all the remaining inequalities, all the remaining statements, each one of them is a consequence of the given inequality. That is, each one of them is necessarily true. That is the explanation, and we just simply write like this. The remaining statements are all necessarily true. Okay, and the solution ends here. Then exercise 4. If -1 is less than y minus 5 and y minus 5 is less than 1, then which of the following statements about y are necessarily true and which are not necessarily true. You have to understand that the actual solution to that to the previous exercise is not this much. You have to in fact write all the justifications. I have just given hints to hints about how to write those things. You have to complete this solution, so it's incomplete. In this form it is incomplete. Okay, now what are we given about y? For y also some statements are given. A, 4 less than y less than 6. B, minus 6 less than y less than minus 4. Y is greater than 4. D, y is less than 6. E, 0 is less than y minus 4 and y minus 4 is less than 2. F, 2 is less than y divided by 2 and that is less than 3. G, this is less than 1 by y and this is less than 1 by 4. And finally H, the absolute value of y minus 5 is less than 1. Okay. Note that the given inequalities imply you add 5 throughout, add 5 to all the terms, that we can do. The inequalities will not change direction, and we will have 5 minus 1 4, y minus 5 plus 5 is y, this is less than 6. So you can immediately see that A is necessarily true. Okay, hence the statement in A is necessarily true. Since we are encountering A first, so we are disposing of this case. Then we come to B. However, the statement in B is not necessarily true. Because if you take y equal to 5, then minus 1 is actually less than 5 minus 5, which is less than 1, because 5 minus 5 is 0. But you cannot take 5 here. But the inequalities minus 1 less than 5 less than minus 4 are not true. Are not true means actually both of them are false. This is false and the second one is also false. So that's why B is not necessarily true, and all the remaining statements are necessarily true. And it's up to you to verify that the remaining statements are all necessarily true. Let's just see any one of them quickly, namely this one, apparently the most, we cannot say it's the most difficult one, because the way the initial inequalities are given, they directly imply this. So this is necessarily true. Say we take this one, y is greater than 4. We have already seen that the given inequalities imply these, and these again imply that y is greater than 4. So that's why this is necessarily true. Just like that, this is also necessarily true, and the remaining statements you can verify. Okay, so the solution, I end the solution like this. Okay, now a few words about necessary and sufficient conditions. If you have an implication like this, an implication is a statement that looks like this, where P is some statement, Q is some other statement which may or may not be P itself. we already know that this is called the hypothesis of the implication and this is called the conclusion. If say the implication is true, then we say that Q is necessarily true for P. That means if P is true, then Q has to be true. It's a necessity that Q be true. And at the same time, let me write it like this: Q is necessary for P to be true. That is, if P is true, then Q must also be true. In the same situation, we say that P is sufficient for Q to be true. That is, truth of P is sufficient or enough to conclude that Q is true. Because we in mathematics we most often encounter implications, that is, we are given some hypothesis and we have to prove some conclusion, or double implications, namely a statement like this: something happens if and only if something else happens. Then we have to prove two implications. After all, we are always encountering implications. So you have definitely come across languages like this that prove that, for example, you can, what example can I give? Say P is a prime. Let me give a very trivial example, okay. P is a prime implies P is greater than 1. Prime in the ordinary sense of prime numbers that we know, okay. Then this is a true implication. If P is prime, then P has to be greater than 1. That means if P is prime, it's necessary for P to be greater than 1, and primality of P is sufficient to tell us that P is greater than 1. However, this does not imply the converse, that is, P greater than 1 does not imply that P is a prime. P being greater than 1 is not sufficient for P to be prime. We need something else. For example, 4 is also greater than 1, but 4 is not a prime. So this is not a sufficient condition for this one. This is only a necessary condition. Had the two been equivalent, then any one of them will be a necessary and sufficient condition for the truth of the other. Okay, so this is some, the logic behind all these things that we are saying when we say necessarily true, something is sufficient for something else. Okay, next in exercises 5 through 12, solve the inequalities and graph their solution sets. So these are the inequalities. Here we have to solve them one by one. Minus 2x is greater than 4. This is the first one. First one means the fifth one. Minus 2x greater than, or let me write it properly. Let me show one of them, then you can solve the others. Minus 2x greater than 4. This implies 2x is less than minus 4. Multiplying both sides by minus 1. If you do that, the inequality will get reversed. X is less than minus 2. Multiplying both sides by 1 divided by 2. Now the inequality does not get reversed because 1 by 1 upon 2 is a positive real number, and on this side we will have minus 2. So the solution set is the set of all real numbers, and in fact you can see that you can go back. What is happening here actually? What does it mean for us to write this inequality and then get this inequality? Here when we are writing this, we are assuming that x is a real number that satisfies this inequality. Then it implies that x has to be a real number less than minus 2. And if you go back, if x is a real number less than minus 2, then also x satisfies this inequality. That means the set of real numbers satisfying this inequality is a subset of the set of real numbers less than minus 2, and the set of real numbers less than minus 2 is also a subset of the set of real numbers satisfying this inequality, and that's why the two sets are equal, and because of that we can write the solution set is this: the set of all real numbers less than minus 2, which is this ray, this interval which is a ray. And if you want to draw, we have been asked to draw the graph. The graph will look like this. Here say you have 0, this is the positive direction of the number line, and here you have say minus 2. Then the graph is the set of all real numbers that lie to the left of minus 2, not including minus 2. Okay, so that is this ray. is the graph which extends indefinitely in this direction. It's unbounded in that direction. Now that we have written one solution properly, we can write the others more sketchily, not writing all the details. In fact, we will just barely solve the inequality and that's it. Note that not many of us write the reverse implications, but it's necessary. Otherwise, what happens? It just simply says that the set, if we are using only this direction of the implications, then that just implies that the solution set, that is the set of all real numbers satisfying this inequality, is a subset of this interval, not necessarily equal to the interval. Okay, that much only one-sided implications say. If you are able to reverse the implications, all of them, then only you can say that the solution set is equal to this. Okay, then what is the sixth one? 8, I need ink. And this issue of reversing implications is not true only for inequalities but for equations also. There also we sometimes neglect, in fact most often we neglect this entirely. However, that's why when something else is given along with an equation, say some other condition is also given, say your equation has come from a real life situation where the variable needs a positive answer, say it represents some length or say it represents some number of some elements in a set. In that case, the equation you have, if it turns out to be a quadratic equation, you already know that it will have two roots, and very often one of the roots is negative. So that just tells you that the solution set is a subset of the set of those two roots. But since the solution demands the variable to have only a positive value, only one of them will form the actual solution set. Okay, then this one is 8 minus 3x greater than or equal to 5. So here I am just going to write it in an extremely short manner. You can do whatever you are required to do here, and you will ultimately see, if you subtract 5 from both sides, you will have 3. So 3 is greater than or equal to 3x. So 1 is greater than or equal to x, and that's why the solution set in this case is minus infinity comma 1. This closed ray, I hope it's visible, minus infinity comma 1, 3x 3, yes, then 7. In 7 we have 5x minus 3 less than or equal to 7 minus 3x. So what happens when we add 3x on both sides? We will have 8x on this side, and if we add 3 to that side, on this side also, then 8x is less than or equal to 10. So x is less than or equal to 10 divided by 8, which is 5 divided by 4. So in this case, the solution set is again an interval like this, and you can clearly draw these solution sets. Unlike this one, if you draw this one, the point representing the real number 1 will be inside the solution set. Just like that, this one also 5 by 4 will be a part of the solution set. Then 8, 3 times 2 minus x is greater than 2 times 3 plus x. So here what shall we get? 6 minus 3x is greater than 6 plus 2x. Okay, minus 3x on this side and 2x on this side. So that means 0 is greater than 5x. That is, x is less than 0. So this is the solution set. Note that I am doing it in an extremely short manner. Almost verbally I am just going through all the arguments and trying to find the solution. So naturally I may make mistakes, so you verify all these things. Then the next one, 2x minus 1 upon 2 is greater than or equal to 7x plus 7 divided by 6. Okay. So if we calculate like this, then it will be minus 3 minus 7 is greater than or equal to 5x. So ultimately I have to write minus 10 divided by 6 is greater than or equal to 5 by x, or 5x, or x is less than or equal to minus 1 by 3. So in this case the solution is again an interval, but we have the option of x being equal to minus 1 by 3. So this, it's closed on this side. For 10th one, we have 6 minus x divided by 4, and that is less than 3x minus 4 divided by 2. So the inequalities are getting more and more complicated. Oh, here I didn't write solution. You can start from here. You can multiply by 4. On this side, 3x minus 4 will then be multiplied by 2, because 4 divided by 2 is 2, and we will have this. So 6 plus 8 is 14, is less than 6x plus x, 7x. Again, I am reminding you of the fact that here I am writing double implications, but it's not just a matter of writing. It should be true. You should be able to go from this last step to the first step to be able to write the reverse implications. If at any step you find that the inverse implication or the reverse implication is not true, you cannot write it. Okay, in this case we need the reverse implications to say that this is the solution set. So in this case the solution set is slightly different. It has a left boundary. All these solution sets had right boundary points. So it's this open ray 2, infinity. Two more are there. 11. 4 divided by 5 times x minus 2 is less than this. So what we do here, we multiply on both sides by 15, the LCM of 5 and 3. So on this side we will have 12, because 15 divided by 5 is 3, 3 times 4 is 12, 12x minus 24. On this side we will have 5, so 5x minus 30. So x is less than minus 6 divided by 7. So this is the solution set. Again, a ray with a right boundary. And finally, number 12, minus of x plus 5 divided by 2 is less than or equal to 12 plus 3x divided by 4. So we multiply throughout by, on both sides by 4. So on this side we will have, note carefully that this minus sign is with this entire quotient, not just x. Okay. So minus 2x minus 10 is less than or equal to 12 plus 3x. Minus 10 minus 12 is minus 22 is less than 2x plus 3x is 5x, or minus 22 divided by 5 is less than or equal to x. So here the solution set is this interval. Okay, now next we come to some exercises involving absolute value. Solve the equations in exercises 13 through 18. Okay, so what is the 13th one? Absolute value of y is equal to 3. So we know that when we have absolute value of something, then that the argument inside this y alone can either be non-negative or negative. As a real number, it is either non-negative or negative. If y is greater than or equal to 0, then y is equal to absolute value of y by the definition of absolute value, and that is equal to 3. So this is one solution, and if y is less than 0, then absolute value of y by definition is minus y, and in this case y is minus 3. So we have two solutions of this equation, 3 and minus 3. Then 14. This is equal to 7. In this case we can write find the solutions quickly like this. Y minus 3 is either non-negative or negative. If y minus 3 is non-negative, then y minus 3 is the absolute value, which is equal to 7, which implies y is equal to 10. And if y minus 3 is negative, then 3 minus y is equal to this, which is equal to 7, and so y is equal to minus 4. And now you can substitute these values and see whether you are actually getting 7. 10 minus 3 is 10 minus 3 is 7, so absolute value of 7 is 7, and minus 4 minus 3 is minus 7, whose absolute value is also 7. So yes, so these are the two values of y. 15. Absolute value of 2t plus 5 is equal to 4. So here you can see that 2t plus 5 will be either 4 or minus 4. If 2t plus 5 is equal to 4, that means t has to be equal to minus 1 by 2. This is one value, and if it is equal to minus 4, then it is equal to minus 9 by 2. Minus 1 divided by 2 and minus 9 divided by 2. If you substitute here minus 1 by 2, then you get 5 minus 1, which is 4. Absolute value of 4 is 4. And if you put minus 9 by 2, then you get minus 9 plus 5, which is minus 4, whose absolute value is also 4. 16. This is equal to 1. Okay. So in this case, this is either equal to 1, so t is 0 or 2. You can solve like this, argue like this, and you will ultimately find that the two values are 0. If you put 0, you get absolute value of 1. If you put 2, you get absolute value of -1. In both the cases, the value is 1. 17. 8 minus 3s is equal to 9 divided by 2. Okay, for this one, okay, let's just go through the argument. If 8 minus 3s is greater than or equal to 0, then that implies (16 minus 9). See, to calculate this 7, I had to think for some time. That's what I mean when I say that my numerical calculation is very bad. Is it really 7? Let me just, yes. So S is equal to 7 divided by 6. So one of the values of S is 7 upon 6. What about the other? If 8 minus 3s is less than 0, then so here let's quickly verify whether this is true. If I substitute say 7 by 6 first, then I would get 7 divided by 2. Okay, 8 minus 7 divided by 2. Yes, so I get 9 by 2 because 16 minus 7 is 9. Absolute value of 9 by 2, which is 9 by 2. And if I substitute 25 divided by 6, then 25 divided by 2, and that is equal to 16 minus 25 divided by 2, and 16 minus 25 is minus 9. So this is again 9 by 2. Yes, we have got the solutions. Okay, so these are some equations involving absolute value. Next we have some problems where we have inequalities involving absolute value. Solve the inequalities in exercises 19 through 34. Expressing the solution sets for these equations also we could have written solution sets. For example, for this one the solution set will consist of these two real numbers. Okay, but since we have not, it's not mentioned that we have to write the solutions as a set, so we didn't bother to write them as a set. As intervals or unions of intervals. Also, graph each solution set on the real line. Okay. This one is easy. We already know from some arguments that we have gone through in the text that this inequality is equivalent to these inequalities, where we are using the fact that this represents the distance of the real number x from the real number x from the real number 0. So from that fact we can derive this equivalence, which we have already done in the text. So the solution set is this open interval, and if you draw it on the real line, then it will look like this. You have -2 here and say 2 here. These 2 points will not be part of the set. Everything else in between will form the solution set. So this is 19. For the others we will not write we will not draw the graphs. That is left to you. This is less than or equal to 2. For this one, similarly, just like this one, here the solution set is the closed interval -2, 2, because in place of strict inequality we now have less than or equal to relation. Is less than or equal to 3. You just have to go through the same similar arguments. T minus 1, -3 is less than or equal to t minus 1, which is less than or equal to 3. So if you add 1 throughout, you will get -2 less than or equal to t, that is less than or equal to 4. So in this case the solution set is the closed interval -2, 4. 22. This is less than 1. As long as we are getting less than inequalities, we can apply the similar argument to obtain the solution set. The moment we get greater than inequality, there we have to apply some other method. Okay, in this case, this will be equivalent to these inequalities, which in turn are equivalent to, if you subtract 2 from all the terms, you will have this. So for this one, the solution set is this open interval 23. 3y minus 7, its absolute value is less than 4. Adding 7 to all the terms, we get 3 less than 3y less than 11. Multiplying throughout by 1 divided by 3, we get 1 less than y less than 11 by 3. Our ultimate aim is to make y alone. Okay, is to separate y from everything. That will tell us the conditions that y has to satisfy. So here the solution set is this open interval 1, 11 by 3. Then 24. 2y plus 5 is less than 1. This is the solution set. 25. Minus 1 is less than or equal to 1. So here the solution set is this closed interval. This let's just again interpret what this really means. It means that if you take any real number from this closed interval, that is going to solve this inequality. And if you take anything else, that is any real number from outside of this interval, that will not solve this inequality. Okay, that's what it means. 26. Okay, this is same, it's left to you. 27. 27 is slightly different. Because here we have x in a quotient where it appears in the denominator. This is less than 1 by 2. We start the solution just like any other solution, but in between there is a step whose justification needs something new. Because the situation is a little unknown or a little unfamiliar, so we start with only one implication. Okay, this implies, just like before, this. Up to this stage there is no problem, it's just like what we did before. Also, we can subtract 3 from all the terms. Which implies this becomes minus 7 divided by 2 less than minus 1 divided by x, and that is less than 1 minus 6 is minus 5 divided by 2. Now next, to simplify things, we are going to multiply throughout by minus 1. That will reverse all the inequalities. So now we have 7 by 2 is greater than 1 upon x, and that is greater than 5 upon 2. Now we want to take reciprocals of all the terms, but can we do that? We can do that because note that whatever x is, x cannot be negative. If x is negative, then this 1 upon x itself is negative. But a negative number cannot be greater than 5 by 2, which is positive. So that's why x is positive, and there is, since x is in the denominator of a quotient like this, there is no question of x being 0. X is positive. So x is positive and all the numbers are positive here. So we can take reciprocal, and doing so will again reverse all the inequalities. So this implies 2 by 7 is less than x, and that is less than 2 divided by 5. Now you see carefully, can you go in the reverse direction? From this one you can get this one. Yes, because x is still positive, so you can take reciprocal, the inequalities get reversed. Then you multiply by minus 1 and you get these inequalities, they again get reversed. Yes. Then from here, after that, all the steps you can clearly see can be reversed, all the implications. So that's why this determines the solution set to be this open interval. Okay. 28. So this was 27, then 28. 2 divided by x minus 4, its absolute value is less than 3. It's left to you because this is similar. 29. Okay, now again we have got something new. We don't have less than or equal to, we have greater than or equal to. So here this also we have seen in the text, but let's just recall what we saw. This is the real number 0 and we have say minus 4 here and 4 here. What this inequality is telling us is that the distance of the real number 2s from 0 is either equal to 4 or greater than 4. So clearly the real number 2s cannot be here, I mean in between minus 4 and 4 anywhere, because then its distance from 0 is less than 4. This much is 4 and this distance is less than 4, either to this side of 0 or to that side of 0. So 2s must, this portion is not allowed. 2s must either lie on this side or on that side, and it's allowed for us to take the value minus 4 and 4. That also we can have minus 4 and 4 for 2s. So in this case we have 2s is greater than or equal to 4 or 2s is less than or equal to minus 4. From this one, what are we getting? S is greater than or equal to 2 or S is less than or equal to minus 2. It says that any solution to this inequality is either greater than or equal to 2 or less than or equal to minus 2. Conversely also, if you have a real number which satisfies either this inequality or this inequality, you can easily see that this inequality is also true. So that's why the solution set in this case is a union of two intervals. All the real numbers less than or equal to minus 2 along with all the real numbers greater than or equal to 2. That's why before these exercises it has been written, express the solution sets as intervals or unions of intervals. So this is a situation where we have a union of two intervals. Next, 30 s plus 3. Okay, now we will have all the greater than and greater than or equal to inequalities. Let me solve this one. Either s plus 3 is greater than or equal to 1 by 2 or s plus 3 is less than or equal to, you change the inequality. Okay, for the second one you change the direction of the inequality and with the other number you put a minus sign. So this one gives us what? S is greater than or equal to 1 by 2 minus 3, that is minus 5 by 2. Whereas this one gives us S is less than or equal to minus 3 minus 1 by 2, which is equal to minus 7 by 2. So in this case the solution set is minus infinity comma minus 7 by 2 closed interval less than or equal to we have union minus 5 by 2 comma infinity. Never put a bracket like this. I have already said this, I am again saying this. Minus infinity and infinity are not real numbers. They are elements outside the set of real numbers. They are something, but we don't really need them right now. Then 31. Okay, for this one we will get 1 minus x is either greater than 1 or 1 minus x is less than minus 1. That is, x is less than 0 or x is greater than 2. So in this case, the solution set is the union of these open intervals. One more thing, when you are writing infinity, don't do this, okay? It represents something else. It's the symbol for direct proportionality. This is the symbol for direct proportionality or proportionality symbol in general. This is infinity. Infinity is closed. The curve is closed. It's like 8 has collapsed. And if you are writing alpha, it looks like this. These are three different symbols. (32) 2 minus 3x is greater than 5. This one is left to you. 33. Absolute value of r plus 1 divided by 2 is greater than or equal to 1. Okay. Now this is also just like all the other exercises. I mean the previous few, but I want to tell you something about the this inequality. Instead of always writing the condition or the conditions directly, you can in fact simplify the given inequality itself. Note that this is equivalent to this. What have we done here? Here we have used this property of absolute values. Okay, so this inequality is equivalent to this one. This again is equivalent to r plus 1 divided by 2, that is greater than or equal to 1, and that in turn is equivalent to this. Although the simplification, instead of working with this inequality, it's equivalent to work with this one. The simplification is minor, but nevertheless it's a simplification. Its purpose is to show you that some such things can be done to the inequality itself, so that you end up with something somewhat simpler, or maybe if many steps are involved, drastically simpler. Now after this you have to follow the usual route. and that part is left to you. R plus 1 will either be greater than or equal to 2 or less than or equal to minus 2. From there you can find the intervals for R and take their union. And finally there is this number 34. This one, let's just do it. We have if and only if either 3r divided by 5 minus 1 is greater than 2 by 5 or 3r divided by 5 minus 1 is less than minus 2 by 5. Now this is equivalent to, we can multiply throughout by 5. Doing that will give us 15r, just to get rid of these fractions. Minus 5 is greater than 2. Inequality does not change direction because we are multiplying by a positive real number. Okay, so 15r is greater than 7, r is greater than 7 divided by 15. And what about the other inequality? I hope I am not making numerical mistakes. That is always my fear. Here also we can multiply by 5, giving us okay, see, I have made a mistake. I have multiplied by 5, so this will not be 15, no, because 5 will cancel itself and we will have 3r. How awfully. Here also we will have 3r minus 5 is less than minus 2, and that is equivalent to, now since we have minus 2, so this will be 3, that is r is less than 1. So the solution set is r is either less than 1 or greater than 7 divided by 3. That means union this. So this is the solution set which you can easily draw the graph of on the real line. Okay, so there are many more exercises, so we will continue in the next video. So I end the video here itself. So see you in the next video. This is me, Lucifer, from a mathematical room, signing off. Have a nice night.